In this video, we're going to cover function shift rules. And we'll start with the left shift rule. When we replace x with x plus c in our function, the graph will shift c units to the left and have the same shape. And here's an example. We have the function y equal x cubed graphed, and we also have the function y equal x plus 4 quantity cubed. We've taken the x out of x cubed and replaced it with x plus 4. The effect is to shift the graph 4 units to the left. Now let's look at the right shift rule. If we replace each x with x minus c in the function, the graph will shift c units to the right. And here's an example. We have this unusual function y equal x to the fourth minus x graphed in red right here. I've taken each x in this function and replaced it with x minus 3. And look what happened. The whole graph shifted over 3 units to the right. And it has exactly the same shape, it's just moved 3 units to the right. There is also a rule for shifting the graph of a function up or down. To shift a graph up, you just add to the formula. To shift a graph down, you subtract from the formula. And here's an example. I have the graph of y equal 0.125 x to the fourth in the middle here. And it looks like a parabola, it's just flattened out a bit. Now I add 3 to this formula, and I have the formula y equal 0.125 x to the fourth plus 3, and the graph is just moved up 3 units. Exactly the same shape, but moved up. And in the bottom graph, I've just subtracted 4 from the formula, and the graph is shifted down 4 units. Now here's another rule that's used quite a bit. If you multiply the formula by -1, the graph will be reflected across the x-axis. And here's an example. Here we have the graph of y equal x squared plus 2. It's a parabola that's been shifted up 2 units, having points at 0, 2, 1, 3, and -1, 3. Now look what happens when we take the negative of the formula. And here we have the formula y equals the negative of x squared plus 2, which we could also write as negative x squared minus 2, distributing the negative sign. And look at the graph. It's a mirror image across the x-axis. We have the points 0, -2, 1, -3, and -1, -3. We can vertically stretch or shrink the graph of a function by multiplying the formula by some constant c. And here's a nice simple example. I have the function y equal x squared graphed here in red, and I also have a function where I've multiplied the formula x squared by 2 and also multiplied the formula by a half. When we multiply the formula by 2, the graph is vertically stretched by a factor of 2. Instead of the 0.11, we get the 0.12. When we multiply the function by the constant 1/2, as in y equal 1/2 x squared, instead of the 0.11, we get the 0.1 1/2. I say that when we multiply by a number greater than 1, we vertically stretch the function graph, and that's what happened in y equal 2x squared. When we multiply the formula by a number less than 1, we vertically shrink the function graph, and that's what happened with y equal 1/2 x squared. The last function shift rule is the one where we reflect the graph across the y-axis when we replace each x with -x in the formula. And I'll illustrate this rule with an example here. I have the graph of y equal 1/2 x minus 1. It's the equation of a line. I replace x in that linear equation with -x, and I get y equal 1/2 times -x minus 1. And you can see that the graph of the new line is a reflection of the other line across the y-axis. We won't see this rule too much right now, but when we get to the chapter on exponential function graphs, we will see this rule used quite a bit. And now we're going to do an example that uses 3 of the shift rules we just covered. We're going to graph y equal 2 times the quantity x minus 4 quantity cubed plus 1. And we're going to assume that we know what the graph of y equal x cubed looks like. Well, I have the graph of y equal x cubed shown here. It's a graph with an S-like curve. You go over 1, up 1 on the right, and over 1, down 1 on the left. And we're going to use function shift rules to graph our new graph. We've multiplied the function by 2, So that's going to vertically stretch the graph. We've replaced x with x minus 4, so that's going to shift it to the right 4, and we've added 1, which will move it all up 1. So let's look at the new graph. We move that point 0, 0 to the new location 4 to the right and up 1. So we have the point 4, 1 right here. Instead of going over 1, up 1, we're vertically stretching by a factor of 2, so we go over 1, up 2, and over to the left 1, down 2, which would be right about where the equal sign is. And that gives us our new graph. Shifted right 4, up 1, and vertically stretched. And here's a note. Do the vertical shift last. This will always give you the correct result since it will correctly follow the order of operations. For example, if we were graphing y equal negative of x minus 2 quantity squared plus 1, we would reflect the graph down, upside down, shift it to the right 2, and the last thing we would do is just move it all up 1. If we move the graph up 1 and right 2 and then reflect it last, we would get the wrong graph. And here's another note. There was no calculation of points. Just use the rules and move your graph. In this last example, we're going to shift the graph of a function using the function notation. We're given the graph of f of x below. We don't know what the formula is, we just have the graph. But we're going to graph f of x plus 2 minus 1. Well, f of x plus 2 means replace each x with x plus 2, and then we subtract 1 from the formula. Well, this equates to the function shift rules of shifting left 2 and down 1. So that's all we have to do is move each of these 4 points I have shown here, left 2 and down 1. So this gives us our new graph. We take the point 2, 4 and move it left 2, down 1 to get the point 0, 3. We take the point 1, 2, move left 2, down 1 to give the point negative 1, 1. Take the point 0, 1, left 2, down 1 to give us negative 2, 0, and then finally the point negative 1, 1/2, it looks like a half, left 2, and down 1 to negative 3, negative 1/2. We draw a smooth curve through these points and we have our new graph.